Okay, perfect. Well, thank you everybody for joining and just a quick introduction. So my name's Ryan Siegler and I'm a data scientist and data science advocate here at KX. And today, my goal is to give you just a quick introduction to KX and the products that we have, but really want to get into some of the technical details of vector databases and some different use cases, including one quite popular use case right now called retrieval augmented generation, which is a method on how you can connect your own personal data or enterprise data with a large language model and do it at a large scale. So with that, we can go ahead and jump into the presentation. All right, so at KX, we have three different key products. And first off, the sort of core of it all is KDB Plus over here on the left. And this really is the underlying technology that powers both of these other two products. But what this allows customers to do is to build an analytics engine and databases uh, really structured to their own domain specific applications. So you can architect this however you want as a customer. But moving to what it supports is KDB Insights and KDB AI. So Insights is where you're able to enable AI on structured data like time series data, relational databases, things like that. But what we're going to be focusing on today is KDB AI. And what this is a vector database. And it allows us to use AI alongside unstructured data like text, video, images, audio, things like that. So what we offer are a couple different versions. We have a cloud version that's available for use, as well as a server version. And there's a ton of different use cases you can do with this. But really what it boils down to with vector databases is a highly effective, accurate, and fast similarity search. And we're going to get into exactly what that means in a moment. But that's really the crux of a vector database and why it works so well, especially when using it with large language models and generative AI applications. So we're going to dive into vector databases and getting a good understanding of what they can do and the different use cases that you can use them for. So with KDB AI, like I said, it's a vector database, but there's a couple sort of unique aspects to it because as generative AI has really taken off in the last couple of years, vector databases have as well. And you can go out and see that there's many different options for vector databases. So what does KDB have that is unique? And particular, we have a strong presence with temporal data. So time series data is one good example, really relatable to market analysis and things of that nature. But that is one aspect, the temporal aspect that we are strong in as a vector database. And as I go through this presentation, that'll be highlighted a couple different times. So just a little bit of background on like how we compare KDB Plus, the underlying technology, to some other databases out there. DB Engines has us ranked number one, as well as G2 has us ranked up there as well. So just to show where we rank in consideration to some other competitors. Some of the key benefits of KDB AI. So, like I mentioned, the temporal aspect of this, it's really powerful and something that KX specializes in, time series data. We have really flexible search mechanics, so you can decide when you're building your vector database using KDB AI, you can decide how you want to index your data. And we offer several different indexing methods as well as several different search methods that are easy to try out and benchmark against each other. So depending on your use case, you can custom tune how your vector database is going to work. Um, you're able to store many different types of embeddings within your vector database, and I'll talk all about what an embedding is in a minute if you don't know. But the point is you can store all sorts of different types of data within your vector database, not just text or images or videos or even structured data, but all of those, and in some cases, all of those at the same time. And then it's a highly scalable product. So you could use it on the cloud, you can use our server version, and you can get started for free really easily and quickly by going over to kdb.ai. So this is our website. If you swing on over to KDB AI. It's really easy to get started and get signed up. It's free. Yeah, I recommend trying out the cloud version. You can go ahead and just click here to sign up for free, and it'll get you access very quickly to getting started with vector databases. Uh, and one interesting thing is you could sign up for this and use one of our example notebooks that we have in our Learning Hub, and you can get started with a retrieval augmented generation example, I would say in a matter of about 10 minutes. So really easy to get signed up and try it out. And I think it's a really cool way to get your hands dirty with this, but not take too much effort to do it. So definitely recommend go ahead and try that out if you have the time. Also, we have a YouTube page, KX Systems, where we do all sorts of different informational videos about the products and about just generative AI and vector databases as a whole. It's not specifically focused on our products, but our goal is to be part of the generative AI community and share important information and updates and things like that. So one of the things that I do in my position here is do live streams similar to this live stream where I deep dive into a certain technical topic and then present that live on LinkedIn and YouTube. So if you check out our YouTube page and our LinkedIn page, you'll be able to find many different videos that are diving into related topics. And on January 31st, I'm doing one on metadata filtering with vector database similarity searches. So we keep that going. We try to do a weekly or bi-weekly. So check that out and subscribe to the YouTube and LinkedIn pages. That would be great. All right, so now we can get into the fun, the what vector database introduction, what the heck is a vector database, and why would we use one? All right, so and take a look at this diagram here. And what we see is a general architecture of how a vector database is used. And if we start over on the left here, we have our source data. And this could be really whatever data that you have. It could be text, it could be audio, video, doesn't matter. And we want to be able to do some semantic or similarity searches on this data for a variety of different use cases: retrieval augmented generation, pattern matching, recommendation systems, and many other use cases as well. But what we can do is we can take this data and then we can send this through an embedding model. And an embedding model, all that is, it's just a deep learning model that you can get from a variety of sources like OpenAI, or there's many open source embedding models on platforms like Hugging Face. But you just send your source data through an embedding model, and the embedding model creates a vector embedding. So what a vector embedding is, it's just a numeric representation of your original source data. And why would we want to represent our source data in this way? Well, the reason is that numbers are easily machine readable, unlike natural language or raw images. When we represent them as a vector embedding, a computer can easily understand these. And not only that, but the way that this information is embedded, context of the original source data is stored within these numbers. So you're looking at, like if you're looking at text, for example, you would not just have, it's not just keywords that that are stored in this vector embedding, but it's how the words actually relate to one another and are in context to one another. So it holds a lot more like semantic meaning um, than just having like a sparse vector of keywords. So once we have our vector embedding of our data, we just store that in the vector database. And when we have all these vectors stored in our vector database, we're able to do highly effective similarity searches. So what that means is that we can ask a question about our data, and we can do that in natural language. And then it's going to return the most relevant vectors to our question based on the semantic meaning of the underlying vector. So that's really the big sort of benefit of vector databases is the ability to do that similarity search and do it very fast. So if we look at each of these steps and sort of break it down a little bit further, you think about a vector. What is a vector? It's just a really an arrow through space, if you will, and that arrow has a direction and it has a magnitude. So if you look at like a two-dimensional vector, here's an example, or a three-dimensional vector. But the vectors that you can store in a vector database are high dimensional. So you could, have vectors that are thousands of dimensions. And as humans, we can't really picture what that looks like, but computers can process that and process them very quickly. So we want to put our data into this vectorized format. And we can do that through the embedding model. So you could put your pieces of text through an embedding model and get vector embeddings out in what you would store in your vector databases. Now, one thing to consider is that it's possible to embed different types of data. And we can do things like audio, text, and video or images. And you could have specific embedding models that are fine-tuned to be able to handle these different types of data. So in many cases, if you were doing an image similarity search, for example, which might be good, like in the medical field to identify a disease, um, you could have a specific image embedding model that you'd send images through. And those images then would be represented as vectors and stored in that vector database. But what's interesting is, and what I believe will become more and more prominent, is this idea of having embedding models that are multimodal, which means you would be able to put any type of data through the same embedding model and then get vectors out on the other side. And uh, the benefit of that would be that you could store multiple types of data embeddings within your vector database, which means you could do similarity searches across different types of data. So you could look at the similarity between audio and video, or the similarity between text and images, all in the same space at a very high speed. So you can sort of just easily imagine this as a vector database. It's a space that has many different vectors in it. And when then, as a user, we want to query this database, maybe ask a question about what is going on in this database, what is the data that's held in here. We can do the same thing as we did before, which is input our natural language query into an embedding model and then get out our query vector. And now we have our query that the user is asking in a vector format. And what this means is that we can compare the query with the vectors in the vector database. So when we have both of these things together and we can compare them, that means we can do a similarity search between the two. So when we're doing a similarity search, we are looking for the most relevant and the most similar vectors to our query vector. And there's several different methods that we can use to do similarity search here, including Euclidean distance, cosine similarity, and dot product are the three that KDVAI offer right out of the box. And depending on your use case, of course, you could sort of experiment with all of these and find which one works the best. But the output is you're going to get your top k vectors returned, or your most relevant vectors returned. In this case, we're looking at k equals 3, so we would return the top 3 most relevant vectors. And this is just a little explanation of the different similarity methods that we have. Cosine similarity is you're taking a angle between the two different vectors. So you'd be looking at the angle between the query vector and then all the vectors in your vector database. The smaller the angle, the more relevant they are, and the more related they are. Euclidean distance is just looking at the actual distance between vectors. The shorter the distance, the more related and similar they are. And then dot product takes a look at the angle as well as the magnitude. So all of these different methods could work well, or maybe one could work better than the other. It just all depends on the use case that you're trying out. So I recommend doing some experimentation as you get familiar with your data. Okay, so that was sort of a explanation of vector databases and how they work. But how can we improve how that vector search happens and improve the speed even further than it already is? And the reason I think this idea is important is because you can compare two pieces of data with a like a transformer deep learning model and get a really accurate representation of how similar they are. But the problem is that is quite a expensive and time-consuming process to do that. With a vector database, you're doing very fast similarity searches. But even with those fast similarity searches between vectors, as you scale this up to like billions of vectors, it's still going to take a decent amount of time to find the most similar out of all those vectors. So one way we can improve this, especially as the number of vectors in our vector database scales up drastically, is use metadata filtering. And I think this is a pretty well-known concept if you've worked with databases before. And I would say it's similar to like a SQL where statement. And all that means is that when the user queries our vector database, they can offer the query vector, which is the vector of their question that they're asking, but they can also offer some custom filters alongside their query. And what would happen in this instance is a method called pre-filtering, where we go ahead and set certain filters on our vector database, and the uh, the objects, the vectors that do not meet those requirements are not considered during our similarity search. So if you look at these two steps right here, we're actually reducing the number of vectors that need to be searched over because they do not meet that filter that the user specifies. So this is great because number one, it's getting rid of a lot of the vectors in that vector space, or not considering those vectors during our similarity search. But number two, it's going to be searching over far less vectors. So you're going to get an increase in accuracy because you're only going to be searching over the vectors that meet that requirement, that filter. And then you're going to get an increase in speed because overall you're searching over less vectors in total. And then, similarity search works the same way where we're looking for the top k equals 2. These are the two most similar, and we get that output. So this is metadata filtering. It's a method that's built in to KDB AI. There's many different filtering operations that you can use, and it's easy to use. And you're going to see major benefits if you use it, especially if you're working with many, many vectors, like millions or billions of vectors. You'll see an increase in speed and accuracy there. All right, so the last concept I'm going to dive into today is retrieval augmented generation, or otherwise known as RAG. And you might have seen something about this on LinkedIn or heard some people talking about it as it relates to generative AI. But large language models, they are really powerful and they're really useful. But the thing is, they weren't trained on our own personal data. They weren't trained on our enterprise's internal data. And we want to be able to use a large language model to answer questions about that data. But right now, it's not, these large language models, they're not able to do that. So models like ChatGPT, for example, they're not going to be able to answer questions about your own personal data because it doesn't know anything about it. So RAG is a method that allows a large language model to answer questions about that type of data. So within this RAG pipeline, there's two key steps. And the first step is called retrieval. And that's where we look to extract relevant data that we want the large language model to answer questions about. And retrieval is where the vector database comes in handy. And really, the vector database is like the center of the retrieval pipeline, because it allows you to easily find the most relevant data to a user's query. And then those pieces of data specifically are then passed to the large language model for the next phase of RAG, which is generation, which is where we take that relevant data and we inject it into the prompt for the large language model. And then the large language model can answer the user's query with the information that we extracted from our vector database. So this is how you can introduce information that the large language model was not trained on to it, do it very fast and very effectively, and then enable the model to answer questions for our user about that data. So if we look at this architecture, which hopefully will make this concept a little bit more clear, the first step in this is to load our vector database with vector representations of our data. But if we take a step back even further, um, what we need to understand is the goal of this entire pipeline is to introduce our data to the large language model. That's the whole point of this pipeline. But we do this in a step-by-step process. And the first step is to take our data and chunk that data up. So let's say we have some books or some long articles that we would like to put to our large language model and ask questions about. Well, these large language models, they have a limited context window. And that means you can only put so many tokens or so many words into a prompt or into a query for a large language model at one time. So it's unlikely that you're going to be able to put in all of your data at one time into the large language model and ask questions about it. So what we need to do is break that up into smaller pieces. We need to break our data up into more digestible pieces that can be easily introduced into the context window of a large language model. So that first step is taking our data and breaking it up, and that's called chunking. So if you're interested in learning more about this step, I have a whole video out there on the YouTube and LinkedIn page where I break down several different methods for chunking and why we chunk. And I think it's really a pretty interesting concept. But anyways, once we do that chunking, we then send all these chunks separately through our embedding models to get our vector embeddings, and then store these embeddings in our vector database. So at this point, what you have is a vector database that's full of vectors that represent your data. Now, when the user asks a question about our data, that question is embedded the same way that our data was embedded. And then we can perform that similarity search between that query embedding and our vector database. And what this will give us is our top K relevant documents to the query, or relevant chunks of data to the query. So that is retrieval. That's that first step of the RAG pipeline, is getting this relevant and contextual data. And then moving to the second step, we're augmenting the large language model with this relevant and contextual data. And the large language model is able to answer questions about data that it wasn't trained on because of this RAG pipeline. So that's what RAG is at a high level. And one thing I did want to mention about this, especially as new large language models are released and updated, what we're seeing is that the context window of these large language model is increasing. So you can put more and more data at once into a large language model and ask questions directly to it. So that sort of begs the question, okay, well, why would we still need to do this process if we can just put the majority or all of our data into the LLM at one time? Well, the reason is that even though the context window is larger, the more tokens, the more information you pass into a large language model, the less accurate your large language model becomes. And in particular, it's going to have trouble finding information within the middle of that context window. So if you put, several books of information into your large language model, it's going to have trouble finding information in the middle of that. So the idea of using RAG to present smaller and more relevant chunks to it rather than just putting everything in there at once makes sense for this reason. But the second reason is that large language models, because of their underlying transformer-based architecture, which I'm not going to dive into right now, but because of the underlying architecture of how these large language models work, as the number of tokens you put in increases, or as the number of words you put in increases, there's a quadratic increase in processing time that it takes. So it's kind of a double whammy there. You have the processing times increased, and you're not even going to see highly accurate results with a large number of tokens input. So anyways, the whole point of that is, in my opinion, vector databases and RAG are going to continue to be important to presenting your data to a large language model until there's some solution to the problems that I just mentioned. And as of right now, with the transformer architecture, that's going to be a little ways away at a minimum. So, anyways, that's my presentation for the day. I hope you learned something. You found it useful. I really appreciate you coming out and listening. But happy to answer any questions, and please go ahead and connect with me on LinkedIn. I share different posts and articles like this all the time and do live streams as well. So feel free to connect with me on LinkedIn. I'd love that. And with that, I think I'll close out my part of this. So thank you.